In this lab class we're going to look at Bernoulli's equation. We're going to use this formula and we're going to try and predict the flow properties in a pipe of varying cross-sectional area, and we'll end up with an Excel spreadsheet with plots of pressure, flow rate, area and velocity plotted against distance. But in order to get these results we need to look at the equation used. This is Bernoulli's equation, which is basically a statement of the conservation of energy. It says that for an inviscid flow, which means a flow without viscosity, an increase in the speed of the fluid results in a decrease in pressure of the fluid. So this means that in a flow, if the velocity increases, as it's doing so in this constriction here, the increasing in velocity means that the pressure decreases. So the pressure where the velocity is higher is lower than the pressure where the velocity is lower. So the pressure here is low, pressure here is high. High pressure pushes down the liquid in this U-bend here, and you can see the pressure differential here, which is positive, being caused by the effect of Bernoulli's theorem. Now pressure, what is pressure? Pressure is actually the result of momentum transfer between individual particles in a gas. Looking at gases here, airflow, colliding with the surface. All gases effectively are particles or air molecules, or here we've got nitrogen is blue and oxygen is red. These molecules are bouncing around all around us. They're moving in a vacuum. There's no friction. All the collisions are perfectly elastic. When they hit each other, there's no loss of energy. Momentum is transferred from one to another. When they hit a wall, the bouncing on the wall is what causes the pressure. So the faster they move, the higher the pressure. Now Bernoulli's principle, let's look at these. So this is in a stationary situation in the room around you now. All these air molecules are hitting you. Now when air molecules have a net motion, which they do in this picture, the air molecules here are moving from left to right. What happens is that they end up spending more of their energy. So here they are at the beginning. They're jostling around, bashing into each other. They hit the walls. The pressure's high. As soon as they start moving, the some of their velocity energy is in translation. So if you look at what they say here, some of the speed is used to simply keep up with the rest of the fluid. So the jostling or the bouncing on the wall is reduced, and that's the reason why when a fluid increases in speed, the pressure on the wall decreases. This is a really important concept. They give a good analogy here about children in a corridor. So just imagine all these kids bouncing into each other in a corridor. Here they are, and then they hit the walls quite hard. It hurts their shoulders, but as soon as they start running at the same speed, the collisions with the wall, the energy decreases. The actual impact forces decrease because they spend some of their effort running down a corridor. So now let's look at how we generate this graph here. We can if you go to this website mitchellscience.com, there's a good Java animation which allows you to try different profiles and see what happens to the pressure, the flow rate, the area and the velocity. So let's first of all look at the pressure. The pressure is the red line here. If you decrease the area, the pressure is starting to drop here. Decrease it more, then the pressure drops even more. Decrease the area even further, and the pressure drops to a minimum. So in a Venturi tube or a carburetor, for example, where you've got minimal area, the flow speed increases, the pressure drops to a minimum, the velocity is higher, and you can see the area is dropping linearly. Okay, so we're going to try now and use Bernoulli's equation here to try and calculate this graph. We're going to try and calculate the pressure, the flow rate, the area and the velocity for any given section of tube with 4 points. To do that, we'll use Bernoulli's equation, which is a statement of conservation of energy. We have pressure energy, which is the kinetic energy of the molecules in motion, plus the kinetic energy of the molecules in translation, plus the potential energy as a result of height. This is constant, and the 1 here means that the total energy at this point 1 equals the total energy at any other point 2. So at this point 1, the energy is equal to the flow at this point 2, and if there's a change in one parameter, for example if the velocity increases from point 1 to point 2, so if that velocity increases, then something else has to reduce to keep it constant. And in this example, if the velocity increases, then the height doesn't change, so the pressure must drop. And this is Bernoulli's equation, which predicts that outcome. And now in the next video, we'll have a go at producing this graph in Excel.